Hi, this is Jason, and welcome to the next of the videos in my cosmology series. Just to let you know where we're at, this is all about the textbook from Dr. Barbara Ryden, her Introductory to Cosmology, and so we're going to be following through that entire textbook. And if you're just jumping in the middle, please look at the link to the playlist below. That'll show you where you should start so you can get the thing from the very beginning. All right, so what we're looking at this time is Chapter 2, the third section, which is redshift. And redshift is proportional to the distance, which is an incredibly important fundamental observation for cosmology. All right, let's get to it. Redshift, what is it? Let's define this to be this letter Z that you see here. It is the observed wavelength minus the emitted wavelength divided by the emitted wavelength. What does that actually mean? What it means is that if there's a relative motion between the observer and the emitter of this, whatever light it might happen to be, then the wavelength of light will be changed from its emitted wavelength to its observed wavelength. So if it's moving away from us, we should see it be redshift. If it's moving towards us, it should be blue shifted, meaning going towards shorter wavelengths. Redshift means longer wavelengths. So when we look at, say, this galaxy, which is NGC 1068, we see these pink glows in there, and those are from hydrogen gas. And those hydrogen gas clouds are where stars are being formed. And in the center of it, we see that there's some very bright emission lines of hydrogen and helium and oxygen, because this is a starburst galaxy. And in fact, it is an active galactic nucleus. And so when we look at the spectrum below, we see a bright hydrogen emission line right around 6550 angstroms. And this galaxy has a redshift of 0.003793, according to the the NASA Extragalactic Database. And so this emission wavelength of hydrogen, which is H alpha, which is 6562.81 angstroms, that's been redded to the observational wavelength of 6587.74 angstroms. So its wavelength has been lengthened by 25 angstroms. And that's important because that's what the observed wavelength is longer than the emitted wavelength. Remember that what's important here is we see this picture of a galaxy. And this galaxy is far, far, far away, extremely far away, millions of light years away. And yet we are saying that the laws of physics over there in that galaxy are the same that we measure here. And this is the cosmological principle that we talked about before, and that we're nowhere special, meaning the laws of physics are the same there as here. And this spectrum was taken by Moustakis and Kennicott, published in Astrophysical Supplement in May of 2006 in a study of active galactic nuclei. Now, the study of extragalactic redshift began in the 1910s. Vesto Slipher at the Lowell Observatory was doing some incredibly important work in astronomy. In 1912, he was the first person to observe the shift of spectral lines of galaxies, meaning he's the first person to make the observations like the ones we saw in the previous slide. And it makes he's the person who discovered galactic redshifts. And he said they were a Doppler shift, and he said there were some subtle changes and so forth. He thought that was a Doppler shift, and he measured the speeds of the spiral nebulae that he found. And there you can see the various nebulae that he looked at, and there was 10 that are close by. And these are all redshifts. Of the 25 spiral nebulae, and he called them spiral nebulae at the time, not galaxies. He called them spiral nebulae because they were nebulous clouds in his imagery, and they looked spirally. So of these 25, 21 showed a redshift with some as high speeds as you can see from this graph, up to 1,000 kilometers per second. And that's huge. The redshift was interpreted by him as a Doppler shift. And when you look closely, you see NGC 224. That is Messier object number 31, which is the Andromeda galaxy. It shows a blue shift. That's why it's labeled a negative there. It's one of the very, very, very few that actually show a blue shift. Now, Vesto Slipher was one of the most important people in history of astronomy because he's the one that opened the door for us to understand that these nebulae were not part of the Milky Way. And at that time, it was thought that the entire universe was only the Milky Way galaxy. And so he thought that they were probably not part of the Milky Way, but he couldn't be conclusive about it. He also discovered rotation in 1914 of these spiral galaxies or nebulae, simply because he was able to take spectroscopy of it. And on a very personal note, he was responsible for hiring Clyde Tombaugh to make the discovery of Pluto in 1930. And I remember Clyde Tombaugh from my time in graduate school in 1990. He was an old man, and he was a wonderful old guy. I'm glad to have met Clyde back when I was in grad school at Las Cruces, New Mexico. Now, an important thing about the nature of the redshifts that Vesto Slipher found was that this was something he put out there, and people really were understanding what was going on at the time. And Einstein's relativity was playing a huge part in the physics community at the time. Georges Lemaître, who was a Catholic priest, he was also a physicist, a mathematician, astronomer, and a professor of physics at Catholic University of Louvain. He compiled a list of the 42 galaxies whose Doppler shifts had been measured. And he theorized that the recession of these nearby spiral nebulae or galaxies could be explained by an expanding universe, which was going to be confirmed by Edwin Hubble later. But he found that in his list, 37 had redshifts and 5 had blue shifts. And let's just see how probable that is just by chance, because if you took a random sample of the sky and then say 42 galaxies out of the random sample in the sky, and if it was totally random, you might expect half to be coming towards us and half to be going away from us. But to think if it's completely randomly distributed velocity speeds, and 37 of them had redshifts and 5 had blue, let's just take this like we had 42 coin tosses. What are the chances that if you flipped a coin 42 times, 37 times it would come up as heads and 5 times as tails? Well, the probability for that is about 2 times 10 to the minus 27th. That's a very, very, very tiny probability. So this was not random. This is not a random thing. This is some systematic thing. And he made an average radial velocity of all of these and said, well, let's just say it's an average. And the average then said, from his perspective, about 600 kilometers per second. And he used Vesto Slipher's data as well as others in 1927. And he pointed out that this could be resulting from an expanding universe, which he derived from Einstein's relativity. Now, the funny thing is that Einstein, at first, when he learned about Lemaître's conclusions, he refused to accept the ideas because he said that while his calculations were good, Einstein was fully fixed on the idea of a static universe at the time, which was fixed by a cosmological constant, and that was Einstein's idea. But Lemaître came up with this idea and found an estimate for the average distance. And he said, well, if the average distance of these things is just under a megaparsec, say 0.95 megaparsecs, for all these galaxies, along with this expansion of using this as an expanding universe, it gives him basically a Hubble parameter or a Hubble-Lemaître parameter of 625 kilometers per second per megaparsecs. And this is basically the first measure of the Hubble constant. He derived this Hubble's law, then, therefore, and it's now called, as by agreement by the International Astronomical Union in 2018, that it should now be called the Hubble-Lemaître law. And it was the first estimation of the Hubble constant. And this is 2 years before Hubble derived his article in 1927. Lemaître also proposed the Big Bang theory of the origin of the universe, calling it the hypothesis of the primeval atom and also calling it the beginning of the world. And he was greeted with a lot of skepticism at the time. However, when he passed away in June of 1966, he had learned about the discovery of the cosmic microwave background. And this provided further evidence for his original idea and proposal way back in the 1920s. So this is an amazing person who started the ball rolling. Next, we go to Edwin Hubble. Edwin Hubble arrived at Mount Wilson Observatory, which is in Southern California, in 1919, right around the time the 100-inch telescope was completed on Mount Wilson Observatory. At the time that he arrived, the prevailing view of the cosmos again was that the universe was entirely composed of only the Milky Way galaxy. He then looked at the objects that were seen as spiral nebulae with these recession velocities, and he identified Cepheid variables inside of these objects. And Cepheid variables were a standard candle that was discovered by Henrietta Leavitt in her studies of globular clusters. What he found was that if he compared the apparent luminosity to their intrinsic luminosity, that would give the distance from the Earth. And the intrinsic luminosity is dependent on the period of their variability. So you can see here, there's an image of M31, which there's a discovery of one of these variables in 1923 in October, and he followed these variables night after night after night to finding their period of variability. And you can see that in those sawtooth patterns. You can see how long it takes for them to get bright and dim, and that's the light curve. And from peak to peak, the brighter it is, the longer the time between peaks. So this is a very well calibrated distance indicator. And so we used that, found the Cepheids in distant galaxies, used those distant galaxies then to get the graph that we see from his publication in the Proceedings of the National Academy of Sciences in 1929. And what we see is he has found the recession velocity as a function of the distance. Now, he wasn't really sure of the expanding universe, but he was very trepidatious about this at the time. But he did make the good observations and found Cepheids in all of these spiral nebulae, which we'll soon call galaxies, including the Andromeda Galaxy and the Triangulum. And his observations proved conclusively that these things were far too distant to be part of the Milky Way, and therefore were in fact galaxies outside our own. And today we no longer consider them nebulae. The slope of the line that he found with these galaxies, given the distance he found and this recession speed, worked out to be about 500 kilometers per second per megaparsec. And that leads us to the Hubble law, or more specifically the Hubble-Lemaître law, which shows that the velocity, v, is equal to this Hubble constant, h sub naught, times the distance, which is now labeled r. And so we could actually put the redshift in there, which is z, and then that's equal to the Hubble constant divided by the speed of light times the distance as well. But the radial velocity is a function, assuming, so the redshift can be interpreted as a radial velocity or a Doppler shift, and that's where the z becomes v, because z is just the shift in wavelength, but we don't know what the function is. But if we interpret it as a Doppler shift, then we can convert it to that v over c. All right, so this is Hubble's definition, and his first derived value based on observations that he did was 500 kilometers per second per megaparsec. Georges Lemaître made an assumption for a distance of about a megaparsec and got a much higher value. The value for the Hubble constant would be debated for a very long time until it winnowed down to a narrow set of values. Now we're left with two different values for it. But this Hubble law is valid only for nearby galaxies. The farther away we go, we have to use a relativistic version of the Doppler shift. It's also really important to note that, again, the Hubble law, the Hubble-Lemaître law, basically says the farther something is away, the faster it's rushing away from us in this linear fashion. For every megaparsec it's away from us, it is traveling, say, 60 or 70 kilometers per second faster for every megaparsec distant. So the distance is proportional to the redshift. And the farther it is away, the faster it's rushing away from us. Let's see what the implications of that are right now. So what are some of those values for the Hubble constant that we see before? Now, if we look at these three diagrams, we see first on the left, Proceedings from the National Academy of Sciences in 2004. We see that the Hubble diagram for using type 1a supernova as the distance indicator. So there was definitely a recession velocity, and we see the recession velocity as a function of distance, and it's definitely on a line out to about just under a gigaparsec, out to 700 megaparsecs. Hubble's original data is a little red square on the lower left-hand corner. And so we can see that this Hubble relationship wasn't just for local things, but it actually goes all the way out deep into space of megaparsecs. And it's not just Cepheid variables or type 1a supernovae. As we can see, there's things called the Tully Fisher or the fundamental plane or surface brightnesses or type 2 supernovae. And we see the average for the Hubble constant from that particular study of a bunch of things put together to see what the average would be is approximately 72 kilometers per second per megaparsec. That's what we can see in the middle graph. So modern data for Cepheid variables gives a value of about 73 kilometers per second per megaparsec for the Hubble constant. And this agrees well with a lot of other direct measurements, such as these type 1a supernovae, Tully Fisher, which is a relationship between the brightness of a galaxy, of a spiral galaxy, and its rotation rate, type 2 supernovae, and other measurements. But it really disagrees, quite importantly, from the cosmic microwave background and baryon acoustic oscillation studies, which show that it's roughly 67 kilometers per second per megaparsec. And these are two well-established ways of measuring this expansion rate. And they're in direct conflict. And this is known as the Hubble tension. And this conflict is valid to within 4 sigma. So this is a real thing. So people have to figure out, and so it's an area of active research. Many of the areas of the active research are based off of the Planck data from the ESA's mission, the European Space Agency's Planck mission, which had some of the final results in roughly 2018. And they've been analyzed and combined with many things to find that by 2021, that when you look at the cosmic microwave background implication for it, you get a series of range of values that right around 67 and a half or 67 and a third or thereabouts. And that's without the Planck data. Cosmic microwave background without the Planck data shows this. WMAP shows this. But if you have, and then you take Big Bang nucleosynthesis arguments with like the baryon acoustic sky survey done by the Sloan group, then you find that there's also this kind of low value. This is really important because the cosmic microwave background and its imprint from the early universe seems to indicate that the Hubble parameter is much lower than if we take more, quote, recent data by direct measurements. The cosmic microwave is an indirect measurement, but the direct measurements, say from Cepheids or Myra-type variables or supernova 1As or masers or the Tully-Fisher relation, they all definitively show a much larger value of 73.2 or 73 roughly. And that's important. It's also interesting to note that the new gravitational wave astronomy that's coming out can actually provide a direct measurement of the Hubble parameter, and it agrees with both. But in any event, the Hubble tension is a real thing and an area of active research. So we'll use 2 different values for the rest of this to understand the nature of redshift. So there might be some of you around there that says, wait a second, redshift uniformly that we see, and the farther away something is, the faster it seems to be rushing away from us. Wait a second, what is with this Hubble law? Doesn't that violate the cosmological principle? Because we started with this idea ago with the cosmological principle says we have isotropy around one point, combined with the Copernican principle that says that we're not special at any point, implies homogeneity throughout the entire universe. Doesn't this violate the cosmological principle? Because it makes us look like we're a special place, like everything's rushing away from us. And in fact, no, that is exactly the opposite conclusion you should draw. Because if we are not at any special place, then this is exactly what you should see in a homogeneous universe that's expanding uniformly. So if we see it, then it doesn't matter where we are. If we were 200 million light years to the right or left or up, we would still see this thing. And in fact, any observer in the universe anywhere will see this effect. So the cosmological principle is not denied by this. In fact, it's strengthened by this idea. To see the effect of the expansion of the universe in a homogeneous and isotropic way that is uniformly expanding, let's actually make a diagram of, say, 3 galaxies. And each of the galaxies may have started from a distance that's the deep blue triangle in the middle, and then the universe is expanded to the light green triangle. And so each of these galaxies has rushed away on its red arrow from each other. Now, there's not any center to this point. This triangle is completely arbitrary, and if I change the triangle to a different set of three galaxies in a different place and rotated them differently, it doesn't matter what orientation, where I place the galaxies, anything, there's no center to this expansion. It's a very important thing. An observer in any one of these three galaxies will consider themselves to be at the center of the expansion just like we do. It's a very important thing. But we're just checking the uniform expansion of space between three of them. So first we define the distances. R sub 1, R sub 2, R sub 1, 2, R sub 2, 3, and R sub 3, 1. Those are each defined by the difference in the vectors. That's what those little bars are, and that's what the vectors are. R1 with a little arrow on it is a vector. Now, it's true that we do have to have some point of origin for every vector, but since we only care about the distance between 2 points, and therefore the difference between two vectors, we actually don't really care about the source or origin point of that vector. In fact, it works out that since there is no center to the expansion of space-time, that we don't really care where we choose the origin for it. And it doesn't matter anyway for this purpose because we only really care about the distances between any two galaxies. R1 minus R2 vector, and the absolute value of that is equal to the distance R1, R2. Same for the other three distances as well. And we let all of those things vary with time. As we let them vary with time, we say now on the right-hand side, those three equations, we show how they vary with time in a uniform and homogeneous manner. So R sub 1, 2 as a function of time is equal to A times some t, well, not times some t, A as a function of time, times the distance that it was at some time initial, t sub 0. And so that A sub t, A of t, scale factor is just a scale factor for the expansion, and all distances grow or shrink at exactly the same rate and with the exact same history. So they all start at some R sub 1, 2 or 2, 3 or 3, 1 at some t naught. We don't care what that time is. It can just be a go, or it can be now and just let it progress into the future. And the scale factor applied to all three is the same. And so that preserves the triangles from the smaller triangle to the bigger triangle. And if we let it go further, the triangle will be preserved as well. All the angles will be preserved. The ratio of the angle, and side rules that you remember from high school geometry, those will all be preserved as time goes on. All right, so now we can then look at the nature of this expansion and how fast things are moving and what the rate of change is. So all of them are going to be having the rate of change being the same, but we can describe v, meaning the velocity of the change, but the v's already have a direction because we have v as measured between galaxy 1 and galaxy 2, and the v measured between 2 and 3 and 3 and 1. All those things are some change in time, dr 2 dt, which is the change in the distance with respect to time. And that's equal to the rate of change time derivative of a of t. And so I've shortened the notation to dot a because that's a standard notation for derivatives with respect to time specifically. And you still multiply that by the initial distance r sub 1, 2 at time initial. So that looks like a whole bunch of things together, but really it's two things. The rate of change of the scale factor, a dot, times the initial distance, which is r1, 2, time of at the time 0. Notice we have three equations. They all have the same exact appearance. But now we take the original equation for the derivation for the distance and we plug that back in, and we find that a dot over a times then r1, 2 of t. So now we're not looking at it from the respect of the initial time, but as it evolves, we have this funny thing in there. So the velocity, the speed, v1, 2 of t, is equal to the distance, 1, 2 of t, as a function of time, times this ratio of the rate of change of the scale factor divided by the scale factor. That a dot over a is called the Hubble parameter, and that's its definition. That is the definition of the Hubble parameter, and it maps the entire history of how these distances all grow or shrink at the same rate because they're all doing so uniformly and homogeneously throughout the universe. Didn't matter which three galaxies we picked. It's just three random galaxies at three random locations. Just because I chose a right triangle doesn't mean anything. But if I chose any 3 points inside of this, I would get exactly the same reaction. We could have just done one just to say that, but then you said, oh, wait, why is it just one? So remember, this triangle could be oriented in any way you can possibly imagine. It will always show this rate. Again, this is the result of the homogeneous isotropic expansion utilizing the cosmological principle we talked about initially. Now, if we look carefully at that Hubble relationship, which is the velocity is equal to some constant times the distance, meaning kilometers per second per megaparsec. And so if you have some distance, you get the Hubble constant and equals the velocity. But if you look closely at it, it's kilometers per second per megaparsec. So we really have kilometers per megaparsec per second is another way of looking at it. But kilometers per megaparsec is that's a distance compared to a distance. So that's some scale factor in there too. That's just changing kilometers per megaparsecs. Therefore, we can then try to solve for a time. So if we take the distance to an object divided by its velocity that's rushing away from us, and we notice, wait a second, the velocity is simply equal to the Hubble constant times the distances cancel out, and we get the inverse of the Hubble constant. And that gives us a time, a characteristic time. Now, if we use, let's say, the Planck mission's value for the Hubble constant, which is, say, 67.949 kilometers per second per megaparsec, then we get the Hubble time equal to 14.488 gigayears or billion years. Now that's interesting. But if let's say, oh wait, well, what about the alternate time? If from Cepheid variables, modern Cepheid variables give us 73.2 kilometers per second per megaparsec, and that gives us a different Hubble time of 13.358 billion years, not light years, years or gigayears. And that makes a big difference because the Cepheid variables show about 13.4, and cosmic microwave background shows about 14.5 billion year old for this characteristic Hubble time. That makes the Hubble constant important because that's almost a billion years of difference in the Hubble time. So, but the really important thing about the Hubble time is no matter what its value, it still has the same interpretation between the Cepheids and the cosmic microwave background measurements. If you go back in time, a time length of the Hubble time by the cosmological principle, every galaxy that existed was cramped that we see in every direction would be crammed on top of each other in some tiny volume of space. And so this is where Georges Lemaître had the idea of the primeval fireball or primeval atom. And this was extremely controversial in the 1920s, but is no longer controversial today. So the Hubble time provides us a characteristic time of the universe. Taking a closer look at Georges Lemaître's idea of the Big Bang, basically a Big Bang model of cosmology is one where everything starts out from some initially extremely dense state and then goes to a much, much lower density state due to this uniform and homogeneous expansion of spacetime. All right, so that's interesting. So how does this Hubble time that we just talked about compare to, say, old stars? Some of the oldest stars that are known are about 13.5 billion years old. And the oldest stars that we know are some of the halo stars in the Milky Way. And we know that they're old because their spectra are extremely metal poor. And metals for astronomers are any atomic element other than hydrogen and helium. That's all metals. Metals because they provide electrons when they're ionized. So as of this recording, the oldest known star has this really long name of 2 mass J 1808-2002-510-4378. Now, its metallicity is extraordinarily low. And metallicity is defined by the logarithmic ratio of how much iron there is compared to how much hydrogen there is in the spectrum. So there's some very prominent iron lines and very prominent hydrogen lines in stars. And so when you look at that, you say, oh, what's the prominence of these lines, these spectral lines in the spectroscopy of the stars? And the logarithmic difference is less than -4, which means that this star has 1/10,000th of the metals of the sun. And I don't just mean like aluminum and magnesium and iron. It means everything. Anything heavier than helium has 1/10,000th of these atoms. So it's very, very, very metal poor. And Therefore, it's made up only of the primordial materials, and it's one of the oldest population 2 and possibly a population 3 star in the Milky Way. And the estimate is that it's 13.53 gigayears or billion years old. So, in addition to those things, individual stars, Milky Way globular clusters have roughly ages around 12 billion years or 12 gigayears. What I've shown here is a picture I took with eye telescope, and this is Messier Object 13, a globular cluster, a beautiful one in the summer sky. And it's pictured here. It's about 11 and 11.6 gigayears old. Now, this one crazy one, the 2 mass, is an interesting one because there's 3 different populations of stars in the Milky Way. There's Pop 1, Pop 2, but there's the third Pop 3, which shouldn't exist in the Milky Way. Population 1 stars are very, very, very metal rich, and they are the youngest stars. Population 2 are older stars made from much older material when there was less and less processed material, less carbon, nitrogen, oxygen in the galaxy. Population 3 should be made only of hydrogen and helium and are the first stars. Now, this 2-mass star has extremely low metallicity, but it's in a binary system. So maybe it's a population 3 that is a binary system. And population 3 binaries could be around today due to mass transfers when one of the stars in the binary aged, filled up during the asymptotic giant branch, expanded to a very large size, and dumped some material from one star onto the other, altering its future history. And so therefore, it could last longer because it lost some of its mass, and therefore it's around still today. And this is a new idea that came out about 2014 or so, is that some population 3 stars could be in the Milky Way if they're in binaries. I'll put a link to that 2-mass star and the population 3 binaries in the Milky Way in the description below. Okay, but for the Hubble time, this raw number really isn't the final word. The Hubble time could be wrong for a number of reasons, at least these 2. Gravity seems to work, and galaxies have mass, and that means there's an attractive force between galaxies that would slow down the expansion. And therefore, if that's the case, if it has slowed down, then the universe was expanding faster in the past, and therefore the universe would be younger than the inverse of h naught. All right, let's go through that again, just so we make it. So if it's slowing down the expansion, that means the universe is expanding faster in the past, which means that it's younger than h naught. H naught says it's a constant expansion, right? But that expansion rate could be changing, and there's reasons to think why it will be changing, and we will learn that it is changing throughout the rest of this course. Next, if there's a cosmological constant or something like it that's acting to speed up the universe's expansion, then that would lead the universe to being older than the inverse of h naught. And which one of these processes dominate? Is it the slowing down or the speeding up? Which of these dominates we're going to explore in later videos, and we'll construct toy universes and watch how their expansion histories change with time. And that's really interesting because that's really our study is how do we know how fast the universe is expanding or contracting? Not just this Hubble constant, but the actual form of the Hubble parameter, because when we looked at that originally with the triangle, there was no constant to that. That could change by any rate. The scale factor is just a function of time, and it can change with time. Likewise, we can also look at a characteristic distance size scale of the cosmos, and that's called the Hubble distance, which is the speed of light times the inverse of the Hubble constant. And for value of, say, the ESA Planck mission of 67.49 kilometers per second per megaparsec, that works out to be about 4.442 gigaparsecs, which is approximately 14.5 billion light years. So that's a typical size scale for a Hubble distance, meaning what's a Hubble distance? If you take everything that's within a radius of 14.5 billion light years, a Hubble time ago, everything was all in the same place. Everything that's inside that radius around us was on top of us at that time, a Hubble time ago. But let's just take a different thing. By comparison, the Cepheid studies, which is roughly 73.2 kilometers per second per megaparsec, then we get a Hubble distance of about 4.096 gigaparsecs, which is 13.36 gigalight years. And if you compare 13.36 to 14.49, Yeah, you're seeing that this Hubble tension is an incredibly important thing because with Cepheid variables, we're seeing a much smaller Hubble distance than we are with the cosmic microwave background. This Hubble tension is having some incredibly important results for really basic ideas about the characteristic size and age of the cosmos. Next, we can look at the result of the characteristic size scale of the universe due to an expanding, homogeneous, uniform expansion of the universe, is that helps us solve Olbers' paradox. This is our resolution. Remember from the other time that we found that the characteristic fiducial size scale is about 10 to the 18th megaparsecs. If the universe is infinite and filled with stars, how far would we have to look in order to see a star? It's about 10 to the 18th megaparsecs. Oh, and incidentally, for those of you following at home, Olbers' paradox is really only described for visible light, and it doesn't consider the cosmic microwave background. If we could see in microwaves, the universe would be uniformly bright at the temperature of 2.7 Kelvin, a uniform blackbody. But Olbers' paradox is about starlight, not about the cosmic microwave background. It says, why isn't the sky as bright as the surface of the sun, given that an infinite universe that's infinitely old, an infinitely sized universe that's infinitely old? So 10 to the 18th is the characteristic value that you'd see for if you looked in any direction with this infinite eternal universe. Now, if we can only look out as far as 4,400 megaparsecs, that's really a lot smaller than 10 to the 18th megaparsecs. So the chance that we're going to see a star in our line of sight is simply this distance, this Hubble distance, divided by the characteristic size scale of the infinite universe. And the probability we're going to see that is about 4 times 10 to the minus 15th. That's a really tiny chance. So when you compare the surface brightness due to Olbers' paradox, which would be the surface of the sun, and what we actually see from starlight in the universe would have to be 10 to the 12th times older, and all the stars would have to keep shining the entire time. So this is a really important thing. We know that stars don't live to be trillions of years. We do not think of the universe as that old. So the surface brightness is about 5 times 10 to the minus fourth watts per square meter per square arc second. But the sky brightness, due to starlight, or just light that is not the cosmic microwave background, is about 5 times 10 to the minus 17th watts per square meter per square arc second. It's much, 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 much dimmer. And therefore, Olbers' paradox is solved by the finite age of the cosmos. And because the light has only had time to get to us from 4.4 gigaparsecs away. And there's the solution to Olbers' paradox. Now, it wouldn't be a proper astronomy talk if we didn't talk about an argument. And the big argument against the Big Bang that started very early was the steady state model. In the 1940s, Hermann Bondi, Thomas Gold, and Fred Hoyle were the biggest promoters of a competing interpretation to the expansion of the universe. Einstein's static universe had fallen away because of the expansion that was discovered by Hubble and posited by Lemaître. But the expansion could then have a different interpretation because a primeval fireball, a beginning of all time, was very disturbing to a lot of people, especially these three, and they created the steady state model. And they promoted it based off of the perfect cosmological principle that says not only are there no privileged places in space, why should there be privileged places in time, privileged moments in time? So the Copernican principle, which is no place is special in space, added to no time special in time, leads us to the steady state model. In fact, Fred Hoyle coined the term Big Bang in his BBC Science broadcasts, and there he is in front of his BBC microphone showing how to do science public outreach. And he was an incredible science speaker. So if you had a special moment in time, then you'd have a Big Bang. But in a steady state, since there's no special time, then what you measure for the Hubble constant would be constant for all time. And the cosmic density, therefore, because in the steady state, nothing changes in time, meaning the cosmic density, rho, would be constant in time, rho sub 0. That's also constant. So whatever the density that you measure today would have been the density a billion years ago, 15 billion years ago, 200 billion years ago, and 200 billion years in the future. This clashed hard with the Big Bang model, and both of these showed an expanding universe. So let's look at the mathematics behind it. By supposition, the steady state says that the expansion rate is constant and is proportional to the distance. We can then easily just state that the functional form of v is v equals h naught times r. The v then is by definition dr dt, the derivative of the distance with respect to time. This v is valid for all time. The Big Bang posits that this v can change in time because h naught is only the value of the Hubble parameter today. The Big Bang model states that h varies with time, thus making v having a potentially complicated form throughout cosmic time. But the steady state says h naught is a fixed constant for all time. This physics gives us the extremely simple differential equation that you see, dr dt equals h naught r, which can be easily integrated to give the distance. R is a function of cosmic time. R of t is proportional to the exponential of the Hubble constant times some cosmic time t. With a functional form of an exponential where v is equal to the derivative of the distance with respect to time, then we can then say, wait a second, if you take r, which is the distance, and run it backwards in time, meaning getting it smaller and smaller and smaller, we find that to get to 0, that we have to go back an infinite amount of time. So time has to go to negative infinity for r to go to 0. So therefore, in the steady state model, the steady state universe is infinitely old and has no beginning. Okay, so let's say it has no beginning. What is the current size of the universe? That's its volume. In order to get the volume of the current size of the universe, which has a characteristic length of the Hubble length, we of course take 4/3 pi r cubed, where it's a spherical volume centered on us. And if you cube that r, which is an exponential, you simply multiply the exponent by 3. So the volume is proportional to the exponential of 3 h naught t. Now, the density of the universe currently, the critical, is pretty close to the critical density, which is 5.9 times 10 to the minus 27th kilograms per cubic meter. If we keep that constant, matter would have to be continuously created inside that volume because that volume is expanding, right? So the matter that needs to be added in the steady state model, m dot steady state, is equal to, well, the volume change with respect to time. That's what the dot is, the change with respect to time, times the density. So the volume times the density, well, that's equal to, what's v dot? That's just the derivative of the exponential. And that is simply 3 times the Hubble constant times the volume times the density. So if we then say how much matter must be created per unit time, per unit volume, we get 3 times the Hubble constant times the density that we see today. And that's equivalent to about 1.74 times 10 to the minus 27th kilograms per cubic meter per gigayear or per billion years. So that's kind of a very tiny number. Can we make that relate to something? Sure. One proton is worth 1.67 times 10 to the minus 27th kilograms. That's the mass of one proton. And of course, there are 10 to the ninth cubic meters in 1 cubic kilometer, and there are 10 to the ninth years in a gigayear. That works out to be about 1 proton per cubic kilometer per year. That's about what's got to be created in the universe in order for the steady state model to work. You have to create matter, 1 proton for every cubic kilometer every year in the entire universe. Some proton just has to magically come out of nowhere. This is the core need of the steady state model. Long story short, the Big Bang did prevail in this argument. But how? Because the arguments are kind of the same. The people supporting the Big Bang said, creating matter continuously, that seems crazy. And then Hoyle and Bondi and Tom, they said, and Gold said, having everything created all at once, that's crazy. So it's kind of two really crazy ideas. And the universe is doing something crazy, whether it's creating matter continuously or having everything created all at once. Crazy meaning counterintuitive and not insane or wrong. Which one had to prevail? The discovery of the cosmic microwave background is the thing that really put the steady state theory to bed, simply because there's no way for a uniform cosmic microwave background to be created as part of a steady state theory. Also, just as important, is our galaxy evolution surveys, such as this image by the James Webb Space Telescope. This image is the JWST contribution to the GOODS South survey. GOODS stands for the Great Observatory's Origins Deep Survey. Most major telescopes or telescope arrays on the ground and in orbit have imaged this field. There's one in the northern sky and one in the southern. The goal is to do extraordinarily deep imagery of one patch of the sky to study the nature of galactic evolution. The field of view is really tiny, and they're therefore called pencil beam surveys. Since the galaxies imaged here are at great distances, because of light's finite speed, we're seeing them as they were a very long time ago. This survey has found that high redshift galaxies have a completely different appearance than local galaxies. This means there's been galactic evolution through time. In the steady state model, the farther out we go, we should see things exactly like the Milky Way, some things being formed, some mixture of things that are old and young galaxies. But the steady state basically says there should be no special time, so we should see a Milky Way if we look out 10 billion light years away. And we don't see Milky Ways, we don't see Andromedas, we see completely different kinds of galaxies. They are completely different in their appearance, their size, their magnitudes, how bright they are, what light they're emitting, everything. Therefore, the Big Bang idea prevailed due to the existence of the cosmic microwave background and the galaxy surveys, galaxy evolution surveys that have been shown. So we do know that it's expanding homogeneously and uniformly. Both the steady state and the Big Bang could solve that. But if it started in a dense hot state and has been expanding ever since, then the cosmic microwave background is a direct prediction of the Big Bang and not just some arbitrary hack add-on that the steady state model would have to do. The Big Bang predicts it, steady state doesn't predict it. Another really important element is the discovery of dark energy and dark matter. Both of these things will change the rate of expansion, the Hubble parameter, as a function of time. The steady state says it's always been the same, but knowing how the energy density of both dark matter and dark energy affect the rate of change shows that this rate of expansion could not be constant. So therefore, the Big Bang wins again. It's at this point when I give this public talk about the nature of the Big Bang, somebody says, well, what about the edge, past the edge of the universe? What's past the horizon, past the edge? Isn't there something, what's like on the edge of the universe? And that's an interesting metaphysical, conceptual question. But remember, there is no special place in the universe. Therefore, if we look at some distant galaxy that might be, say, 10 billion light years away, they would see the same thing, and they would ask the same questions. So that can be represented by this diagram of the nature of overlapping cosmic horizons. Let's say we're the yellow robot in the center. Our horizon would be the yellowish sort of ball that fades towards the edges. But each of the surrounding robots in each of their own galactic center, in their cosmic centers, each has their own center to their expansion. The red robot and the yellow robot are inside this, have a mutual universe, right? So the red robot's ball goes all the way around in that red ring. The purple robot has its purpley ring, and the blue robot has its blue ring. Each of these are separate cosmic horizons. Each of them sees the same Hubble expansion. Each of them would measure the same Hubble constant and have the same Hubble tension problem. But each of these observers don't necessarily see each other. The yellow observer sees all the three observers, but the red observer only sees the yellow, blue only sees the yellow, and purple only sees the yellow. Why? Because for the purple observer, the blue and red are simply too far away. They're outside the horizon. So the question that you could ask is, how many of these tiled horizons do we need to get the universe? And that answer is not at all well known. In fact, it isn't known. It could be an extraordinarily large thing. It could be a spherical geometry where the radius of curvature on this hyperspherical four-dimensional hypersphere is so large that we feel like our spherical distribution on the surface of that hypersphere is just a tiny fraction of that. But we cannot measure the curvature of the entire universe at all. So it is entirely possible that the universe itself is spatially infinite in extent, but it has a time at which it began. The best way to think about the Big Bang is that it happened in all space at one time, even though that space may very well have been infinite. That is the nature of the Big Bang. And every single observer has their own particular cosmic horizon. And that is a direct result of the cosmological principle and the homogeneous and isotropic expansion uniformly for all observers throughout the entire universe, which would be observers even outside of all of these horizons that we see in this diagram. All right, so what we've got here is a summary of the nature of redshift. The redshift itself is a measurable property that is observed in all galaxies. The farther away a galaxy is, the faster it's rushing away from us. The interpretation is there was a time in the past, what we call the Big Bang, where everything was in this hot, dense state and expanded from there. The expansion is isotropic, it's homogeneous, and it's uniform as per the cosmological principle. This is a fundamental expectation. The redshift is a prediction of the Big Bang. It's also a prediction of other expanding universes models, but the hot Big Bang has won out over all of those models. And right now, today, we believe, even though there is a Hubble tension as to say exactly what the rate of expansion is, and maybe there's things we don't know about the Hubble expansion, or the Hubble Lemaître expansion, or the universe's expansion. There might be things we don't know about it, but there is no disagreement that the universe had a beginning and that it is expanding, and that expansion is currently accelerating. And that's the story of the redshift being proportional to distance. I just want to thank you for watching this and sticking with me. I also want to give a big thanks to my Patreon supporters. They've been fantastic through this thing to help me and give me some guidance and some support. And I'd like you to become a Patreon member too, if you'd like. So please check the link in the video. Also, if you enjoyed this video, please subscribe and hit that like button, share it on all the social media, and please come back because I'm going through the entire textbook of Barbara Ryden's Introduction to Cosmology. And so if you want to see what's going on in the future, please stay tuned and we'll see you next time.